Hello, this is the Mr. Da Maths channel. We'll be going through multiple A-level topics and subjects. I will be teaching you further maths throughout this year, and the first topic that we're going to be learning is complex numbers, which has the reference number 2.12 if you want to look it up on the spec yourself. Complex numbers, first of all, were found as solutions to polynomials. So you need to know how to work really confidently with polynomials and what they actually are. A polynomial is defined as an expression with a variable and coefficients and integer powers. So 4x to the power of 4 is considered a polynomial which is order 4. X squared plus 2x minus 5 is another polynomial, but this is a special name. This is a quadratic, which you have encountered in your GCSEs and possibly even the years below in Key Stage 3. Another polynomial could be 7x minus 5. This is a linear polynomial with a power of 1. In A-level maths, you'll be required to solve some polynomials. Let's take an easy example, such as x squared minus 5x plus 2 equals 0. Solving this, you can use multiple methods, such as completing the square. You could possibly no, you can't factorize this. And you could maybe use completing the square as well. So let's try and solve this. Let's try the quadratic formula because that's the standard approach that you'd use in this scenario. So you need to recall this formula for both your A-level maths and your further maths. And I'm going to write it down here. So recall that this quadratic is in the form ax squared plus bx plus c equals 0. Then you can just sub in the equivalent coefficients into the formula. So minus 5 into minus b becomes plus 5 plus or minus square root, what's minus 5 squared? 25 minus 4 multiplied by 1 multiplied by 2 all over 2 times 1, which is 2. Simplifying this down, what you'd find is you'll have one solution, x1, 5 plus square root of 25 minus 8 all over 2. And you'll have x2, which is equal to 5 minus 25 minus 8 over 2. Simplifying this down further, you'll find the roots of the equation. We all know this, okay? At least we should. Now, in further maths, there's some equations or some polynomials with no real roots, meaning those roots are complex. A complex number is defined as, say, a number z, and it's going to have a real part, let's say 5, and an imaginary part, let's say 3i. We'll go into further depth as to what I is, but it's in this form, so it will be in the form a plus bi. So let's look at a polynomial with no solutions. No solutions, as you'd say in A-level maths. So the example given here is x squared minus 2x plus 5. So we'll try and solve that and see what you'd get. Here we have x squared minus 2x plus 5 equals 0. Let's try and use a different method for this. Let's try and use completing the square. In further maths, if I were to diverge off a bit, you need multiple ways to solve a problem, just so you diverse your mathematical skills. So let's try the completing the square method. What we'll do is we'll move the minus 5 onto this side, so we'll have x squared minus 2x equals minus 5. And recall that in completing the square, you'll half this value so that you will essentially be doing the step that you need to get to the final answer, which is completing the square quite literally. So going again, it will go x minus 1 all squared, but we want this expression to equal this expression, so we'll subtract minus 1, which equals minus 5. So putting all the values to one side, we'll have x minus 1 all squared equals minus 4. Here's where a problem arises, at least for people doing A-level maths. We have the square root of a minus number, which does not have any real solutions. What we can do here, however, is say that I equals root minus 1. See how we had a solution or a definition of z equals a plus bi before? This I is exactly that. So let's apply it here after solving this completely. So one solution is going to be x equals 1 plus root minus 4, and the second solution will be x equals 1 minus root minus 4. Breaking this down, what you can do is you can have 1 plus square root 4 times square root minus 1. And you can do the same here. 1 minus square root 4 times square root minus 1. If you were to simplify this down again, you'll get 1 plus 2i and 1 minus 2i. And these are the complex solutions to this quadratic over here. So taking our equation from earlier and its solutions, you'll find that there's these complex solutions which are conjugate pairs of each other. So what this is known as is a conjugate pair. So if one solution like this exists, then there's always another solution like this. Generalizing this rule for any polynomial which has a solution z, which equals a plus bi, then there's going to be another solution which is written as the conjugate of z, with a bar on top of it, or it could also be written with a star in your exam sometimes, which equals a minus bi. This sign flip is largely due to the quadratic equation. And an interesting thing you can do with complex numbers as well is that you can draw a graph of sorts that's called the Argand diagram. Just like this over here. Here's the origin over here, as always. And what you do is you assign all the real values to what the x-axis would be. So this here would be labeled as 1, this would be 2, 3, 4, and so on. And then this would be I, 2i, 3i, 4i, and so on. And then there's the negative values, obviously. So labeling all that. Now let's try and graph this conjugate pair onto this. What you'll see is you'll find that once we graph this, we'll get 1 plus 2i over here, and you'll get 1 minus 2i over here. You'll see that this point is just a mirror reflection of this point and vice versa. So all conjugates are a reflection on the real axis. Now, making this Argand diagram bigger and seeing what we can do with it is what's essential. As what we'll see is you'll find questions where you'll have to work with the Argand diagram, not necessarily draw anything of sorts. However, you will need to do calculations with them later on. So as always, 0, 0 is over here, and we'll have some complex number in this space over here. Let's call this z again. And z equals some arbitrary complex number 3 plus 4i, just for ease of numbers. So if we were to label this Argand diagram, we'll get 4i on the imaginary axis over here, and you'll get 3 on the real axis over here. The interesting thing with complex numbers is you can also treat them as vectors. This will be useful for calculations later on as well in a topic called loci. So we can draw a line from the origin onto the complex number. This is the distance from the origin to the complex number, as you can see, and it's known as the modulus, typically labeled as r in this diagram. So how you represent the distance from the origin to the point z on the Argand diagram is like this. So this r equals mod z. This is notation that you need to know and you need to be confident with. Another interesting thing that you can label on here is theta, an angle between the real axis and this line over here that we've drawn. We can derive some interesting things from this. For example, another way of writing complex numbers. From your basic trigonometry, you'd know that r, this distance, will be equal to the square root of the real axis, how far it travels along the real axis, so 3 squared, plus how far it travels along the imaginary axis, which is 4 squared. This is just basic Pythagoras theorem. Mod of z equals r, and r cos theta would equal 3. And r sine theta will equal to 4i. So what we can say is z equals a plus bi, but z also would be equal to r cos theta plus I r sine theta. Collecting this together, what you'll get is an extremely important form of the coordinate systems that you're supposed to learn in further maths, and this will simplify down to z equals r, factoring it out, cos theta plus I sine theta. You need to be able to be confident with this form and this form. Another interesting thing you can do with this is you can dumb it down even further. You can say that there's a distance from the origin and then there's also an angle from the origin. So you can write it in this form. These two coordinate systems are called the polar forms of this. So there's also calculations with complex numbers that you need to do. This involves adding, subtracting, multiplying, dividing, and doing square roots of these numbers in all forms. First of all, adding and subtracting is quite simple. You'll have, let's say there's a complex number z, which equals a plus bi, and w, which equals c plus di. If you're going to add them, then writing it like this, you'll have all the real parts added together, a plus c, and you'll have all the imaginary parts, which is b and d, added together separately. So the imaginary parts do not affect the real parts. Same thing with subtraction. So if you have z minus w, you'll have a minus c, and you'll have plus bi minus di. This rule applies everywhere. It's just quite simple to add and subtract. You just add or subtract the imaginary parts and the real parts. Multiplying is a little bit trickier. So if you were to multiply these two numbers, so multiplying with complex numbers is a little bit trickier. You need to be good with expanding out brackets. So let's take an example. We'll have z equals 3 plus 4i, and we'll have w equals 1 plus 2i. So let's take z times by w. So z would be 3 plus 4i times w, which is 1 plus 2i. Expanding this outwards like you normally would with brackets, you'll get 3 times 1, which is 1, 3 times 2i, which is 6i, 4i times 1, which is 4i, and 4i times 2i, which would be 8i squared. You can expand on this term over here, where I squared is equal to minus 1. This is because we know that I is equal to square root of minus 1. So if we're to multiply I onto itself, we'll be multiplying square roots by each other, and we will get minus 1 as the answer. So this is the same as saying 8 times minus 1. So the final expression will be 3 plus 10i minus 8, which would be minus 5 plus 10i. Expanding on this, what you'll find is that I always returns to itself after you multiply it by a certain time. So let's see when that happens. We'll have I, which is equal to square root of minus 1, I times I, which equals to minus 1, then I times I times I, which is equal to minus I, and then I times I times I times I, which is equal to 1. And then multiply again, I times I times I times I times I, you'll get I, which is square root of minus 1. See how it repeats after every 5 times? What we can use this fact as is we can generalize this. We can say I to the power of n equals some value depending on that value of n. And there's a trick to finding that. Putting this sort of idea, this sort of phenomenon into the Argand diagram, we'll see that you'll see some sort of like cycle between I, minus 1, minus I, and 1. So drawing the diagram now, you'll see that it kind of rotates between these values. So if you were to multiply I by I itself, you'll get minus 1. So 1 arrow represents a multiplication by I. If you were to multiply minus 1 by I, you'll get minus I. If you multiply minus I by I again, you'll get 1. And then multiply one more time and you'll get I. Generalizing this, you can say that I to the power of n equals some value. If you were to divide n by 4, you'll get some sort of remainder, 1, 2, 3, or 0, and you can determine using that what value it's going to end up at. So let's define that as r, and if r equals 0, then it's I. If it's 1, then it's minus 1, 2, then it's minus I, and 3, it's 1. Division in comparison is far easier. It uses a technique that you've learned in GCSE and possibly even in Key Stage 3. Remember how you might have a square root in the bottom of the answer and you were asked to rationalize the denominator? This is the exact same concept here. So, I mean, it's easier to show it with an example rather than use a general rule as I've done up until now. So, let's say you have z, which equals 2 plus 3i, and w, which equals 1 plus I. To calculate z over w, what you do is you'll have to put it in you'll have to substitute first. So substituting 2 plus 3i in, you'll get that, and then substituting that in, you'll get 1 plus I at the bottom. So the key thing here is that you'll essentially be multiplying, let's do it down here. You'll essentially be multiplying by the conjugate to this. So you'll be multiplying the top by 1 minus I and the bottom by 1 minus I. So if this was a square root, the bottom would be, well, the square root here, imagine there's a square root here, this would be cancelled out if you were to multiply it like this. The same thing happens with a complex number. So let's see what the final outcome would be. We'll get 2 plus 3i times 1 minus I over 1 plus I, 1 minus I. It's good practice to check whether the expression you ended up here is the same as the expression here. And we can see that we can cancel the minus 1 minus I out, so the expression stays the same. So, expanding the numerator, you'll get 2 minus 2i plus 3i minus 3i squared over 1 minus I squared. This I use the difference of squares formula. It's handy that you remember these formulas for the exam because they save time. So writing it down here, a plus b, a minus b equals a squared minus b squared. We learned earlier that I squared equals minus 1, so we can basically just simplify this entire expression down into just a real part and an imaginary part. And if you do that, you'll get 5 over 2 plus 1 over 2i. It's slightly more useful for you to basically split the fraction because you'll show that there's a real part and then there's an imaginary part. Because if you were to simplify this down, you'd actually get 5 plus I over 2. And that is correct, but it's just more useful in this form. Another way to essentially divide and multiply is using the r cos theta plus I sin theta form. This is far easier, although it does require you to memorize the formula. So let's say z equals r cos theta plus I sin theta, and w, which I'll do in a different color, just to show you, w equals, let's actually do r1 here to distinguish between the magnitudes. We'll have r2 cos alpha, because it will be a different angle, plus I sine alpha. So if we were to do z over w, what you'll see is you'll find that it's the same as saying r1 divided by r2 times by the cos theta minus alpha, so in brackets that would be cos theta minus alpha plus sine theta minus alpha. So breaking this expression down, basically you're just subtracting the angles and dividing the modulus of these two complex numbers. Intuitively, this is also almost the exact same thing you do with multiplication. It's just you add the angles and you multiply the modulus. So if you were to write an expression for that, what you get is ZW times, well, ZW equals R1 R2 cos theta plus alpha plus I sine theta plus alpha. So this is a much easier form to work with. Now let's move on to square roots. This involves probably the most algebra that you're going to be using in this topic, and it's probably the hardest thing that you're going to be doing. So let's start with an example first of all. let's say that there's a complex number z, and z equals 3 plus 4i. Just a simple one, okay? And we're going to say, what does the square root of 3 plus 4i equal? At first glance, you might not see much of a method to solve this, but let's look at this in a more algebraic sense. So let's say that the square root of z equals some arbitrary complex number w. So now we can say that root 3 plus 4i actually equals w. You may still not see some sort of method over here. What we can do is we can say w squared equals 3 plus 4i. We can square both sides. Now, here's the interesting bit. You can actually say that w, it equals a plus bi. So you can do another substitution. You can say a plus bi all squared actually equals 3 plus 4i. Now there's a way to go by and actually solve this problem, because this expression is the exact same as that one over here, right? But this is much harder to just think about solving than this. So going even further now, you'll expand this. That's the logical thing to do, obviously. So using the formula again, just to save time, you'll get a squared minus b squared plus 2ab equals 3 plus 4i. Actually 2abi, sorry. So remember how I said that earlier on, the imaginary parts do not affect the real parts. So what you can do here is you can say that these real sections over here add up to 3. So you can say a squared minus b squared equals 3. And you can say that this section over here adds up to the imaginary part, which is 4i. So you can say 2abi equals 4i. Simplifying that down, you can get 2ab equals 4, and then ab equals 2. Now it's just a matter of solving two simultaneous equations. A squared minus b squared equals 3, and ab equals 2. The simplest way to do this is by substitution. We can say that b equals 2 over a, because I moved a to the other side, and then sub that back into this equation. So in a different color now, let's try green. We can say that a squared minus b squared equals 3, and then after the substitution, you can say that a squared minus 2 over a all squared equals 3. Now, if you were to square all this around, simplify this down, you'll get 4 over a squared here, and then a 3 on the other side. Initially, this looks quite scary, but what you'll find is you can do a sort of substitution again. So you can say that a squared actually equals some variable, let's call it u. So this makes the expression surprisingly simple. It goes u minus 4 over u equals 3. Now that we don't want the denominator to be a variable, so we can just multiply everything by u. We'll get u squared minus 4 equals 3u. So u squared minus 3u minus 4 equals 0. This is just a normal quadratic now. Whereas you'd have to work with some sort of weird quartic with some missing variables. So now solving for u, which equals a squared, you'll get u equals minus 4 and u equals 1. Now we can sub the a squared back in. You can say that a squared equals 4. Sorry, I mixed the signs up. A squared equals minus 1. It's usually easier to choose one of these. You don't need to calculate both of them, because if you solve for one of them, you'll get the other one, because you have simultaneous equations. So usually it's easier to choose the real one. So a squared equals 4, a can equal plus 2, or a can equal minus 2. Taking all of this over there, you'll get a equals plus 2 and a equals minus 2. And you know the relationship between a and b. You know that a times b is 2, and b would be 2 over a. So b equals either 2 over 2, which is equal to 1, or b equals 2 over minus 2, which is equal to minus 1. Now, you know that the expression of w is a plus bi, and we've had both variables solved over here. So w can either equal 2 plus I, or w could equal minus 2 minus I. The typical form in which this is written is plus or minus 2 plus I in brackets. And this is the final solution. And this applies to every single question that you'll do regarding this form or this sort of question. And this is basically the method in which you could pick up all the marks, and the preferred method of the